This is the last section in Chapter 3, and what we're going to do is talk about how to create a 95% confidence interval on the difference between two population means when sigma, the standard deviation, is going to be assumed to be the same. Sigma is going to be the same for both those two populations. It is, however, going to be unknown. So to get here, we're going to have to go through the earlier processes that we examined. So we began right here. We said, okay, to get a 95% confidence interval on a single population mean, we take our sample mean plus or minus z alpha over 2 times the standard error, and the standard error was sigma divided by root n. Sigma was known. Then we come over here, and now we no longer know sigma. We estimate sigma with S, with the sample standard deviation. And that's going to bring some uncertainty into the process, because instead of having sigma, which was fixed, we'd have this value of S that would vary from one sample to another, so it would vary. So how do we cope with that additional variability? The way we cope with that additional variability, that Gossett, also known as Student, showed us that instead of using a Z distribution, we could use a T distribution. Now the thing about the Z distribution is it's the standard normal, and all you got to know is alpha over 2. The T distribution, in contrast, you have to know alpha over 2, permissible error, but you also has to know this value of mu, the number of degrees of freedom. We also considered, okay, what happens when sigma is known, but now we're interested in estimating the difference between two population means. So our estimator is going to be theta hat, and theta hat is going to estimate theta, which is just the difference between those two population means. And very similar to what we saw up here, it's going to be the Z value times the standard error. But now the standard error changes because we're not looking at a single mean, we're looking at the difference between two means, and so now we've got this different standard error that is shown here. And then finally, we arrive at where we want to be, which is in this corner here. So how do we get here? Well, it's going to be very similar to what we saw. It's going to incorporate some of the changes that we saw here and some of the changes that we saw here. So what we're going to have is theta hat, just like here. And the reason for that is, of course, we're interested in the difference between two means. And then we're going to need a standard error. We're going to need a standard error. And it's going to sort of look a lot like this, which isn't surprising because in both cases, we've got the difference between two means. But here's the problem. We don't know the standard deviation of the population. So if we don't know it, we have to estimate it. Or in this case where we're displaying variances, we're going to have to estimate it with the sample variance. So as a consequence of using the sample variance, use some index the sample variance instead of the population variance, that means we can no longer use a Z, we have to use a T. So what's this SP squared about? What's that? Well, think of what we're assuming. We're assuming that sigma is unknown, but as I mentioned, we assume that sigma is equal for both populations. We don't know what it is, but we're assuming that it's the same for both populations. And what will happen is when you go into RENR 582, 585, 586, they'll tell you what you can do when you're no longer prepared to make that assumption of equality. For the time being, we're going to assume that although sigma is unknown, it's the same. So here's the problem. When we go out and take our two samples, we're going to get an estimate of variation a variance from the second population and an estimate of variance from the first population, these are based on our samples. It's highly unlikely that these would be the same. So if we've got two different estimates of the population variance, which one of those are we going to use to substitute for the variance that was shown here? And what we're going to do is we're going to combine them. We're going to come up with a weighted, or you can call it a weighted or pooled average of our two estimates of the variance derived from the sample. So back at the whiteboard, we're going to confront that problem that the population variance is unknown. And when we take our two samples, we're going to get two different estimates of the population variance. One from the second population, one from the pooled first population. And what we need to do is we need to pool these two values and come up with an estimate of the population variance. And we're going to refer to that pooled estimate of the variance as that. So how are we going to calculate that? Well, it's going to be a weighted mean. It's going to be a weighted mean of the two sample variances. Variance of the second sample and the variance of the first sample. So, how does one do a sample mean, or excuse me, a weighted sample? Well, let's do kind of a trivial example. Let's consider the color green. How do we get the color green? Green comes from blue plus yellow. So let's say we want to make blue-green. It's going to be green, but it's going to have kind of a bluish tint to it. So what we want to do is have a little bit more blue relative to the amount of yellow. So what we can do is to make our blue-green, we can make that by 5 parts blue plus 3 parts yellow. That'll give us a green, but kind of a blue-green. So another way to look at this is we've got 8 parts in total, 5 from the blue, 3 from the yellow. So what we've got is 5/8 blue and 3/8 yellow. Or we could consider that 5 blue plus 3 yellow divided by the 5 from the blue plus the 3 from the yellow. Or we could say, instead of saying 5, I'm going to change this 5 to the weight assigned to the blue times blue plus weight assigned to the yellow times the yellow divided by weight B, blue plus weight yellow. So the whole idea is that what we're going to do is we're going to try to estimate the population variance. And we're going to do that using a pooled estimate. But S squared P is not going to be the average. It's not going to be a simple average of the first variance, the second variance estimate divided by 2. Nope, we're not going to do that. What we're going to do is we're going to have a weighted average, just like we did up here. We can do something very similar to this. What we're going to have is some sort of a weight associated with the second population multiplied by the variance of the second population plus some sort of a weight associated with the first population divided by the variance of the first population divided by the sum of the weights. So, what are W2 and W1 going to be? What are these weights going to be? These are going to be the degrees of freedom. Associated with the second sample and degrees of freedom of the first sample, respectively. So that's the way that we're going to determine our pooled variance. And so one way to look at this, if we want to do it as a formula, is that our pooled variance is going to be equal to the number of degrees of freedom of the second sample multiplied by the variance of the second sample plus the number of degrees of freedom of the first sample minus the variance of the first sample divided by the total number of degrees of freedom, which is going to be N2 plus N1 minus 2. So, with that in hand, now we can actually do an example. So let's think about doing an example where we've got these two different populations. So we've got population 2, and we take a sample of n is equal to 12. We determined that the average, the sample mean of the second population was equal to 110, and the variance of the sample for the second population was equal to 240. And for our first population, n was equal to 10. Our estimate of the mean was equal to 100, and our variance estimate was equal to 250. So, what's our formula for the 95% confidence interval for the difference between two means when the sample standard deviation, the sample variance is unknown? It's theta hat plus or minus T B alpha over 2 times the standard error. So what's theta hat? Theta hat is going to be y2 bar minus y1 bar, so that's going to be equal to 10. Our t value. Our t value, we're going to get that from our t table. Look at the value 0.025. How many degrees of freedom? We're going to have 12 plus 10 minus 2, and that's going to be equal to 20 degrees of freedom. So let's see if we can find that on our t-table. So what we want is the t-value associated with 0.025 and 20 degrees of freedom. So there's our 20 degrees of freedom, and there's our 0.025. So 2.08596 is the answer. So let's head back to the whiteboard. So now we're back at the whiteboard. We can plug in this value of t, which is 2.08596. All it remains to get is the standard error. So what's the standard error? Standard error, we saw, is the square root of the pooled variance divided by number of observations in the second sample plus the pooled variance, divided by the number of observations in the first sample. And so we've gone over all these numbers. Shouldn't be that hard to calculate. When you go through it all, you get a value of 6.695, and then you calculate all that stuff, and you come up with a 95% confidence interval, which is minus 4.0 to 24.0. So that's the last section in the chapter on 95% confidence intervals.